Hello again. So far we've been talking about matter and motion in fairly ideal terms, that is nice, easily definable objects like spheres or squares or rods or points or those kinds of things. But this is a physics of life course, and all of that stuff is very fine by itself, but it only becomes really relevant when we understand how it applies to important things in the living world, such as adaptation and evolution. And what I'd like to do today is to show you a way in which we can apply principles of inertia, momentum, both translational and angular, to understanding a basic biological phenomenon that we're actually quite familiar with here in central New York. The phenomenon I'm referring to involves the seed capsules of the local maple trees. Central New York obviously has a very rich tree flora, and among them are the maples, several species of maples. And every summer they put out seeds, and here are some examples of seeds. These are known generically as a type of seed coat known as a Samara. And they come in a variety of forms. You can see they usually come out in pairs, like this one right here, joined at the center. But those can easily be broken apart into two pieces, these things float down as the so-called helicopters that we're all familiar with. And of course, they occur in different kinds of shapes. They can have different degrees of hydration, for example. This one is quite green still, and so it has quite a lot of water, and so it's heavier than this one would be, for example, which is dried for a little while and lost quite a bit of its water. You sometimes have some interesting asymmetries in the size of these things. One seed on one side, for example, is quite a bit larger than the seed on the other. And of course, you have different species. This is another species of maple, and it puts out a Samara that has many of the same characteristics, but is different in numerous ways. This seed is quite flat, for example. The seed is in this capsule right here. This seed is quite elongate. The tail of the Samara of this one is quite large, whereas the tail of this Samara is quite small. Now, if you've been in the forest and you've played with these as kids, you of course are familiar with their popular designation as helicopters. And they're called helicopters because they have an interesting spinning motion as they come off the tree. And this is tied into our discussions of translational and angular momentum quite nicely. Let's talk about it theoretically first, and then we'll have some practical demonstrations a little bit later. So suppose you have a Samara, and it looks like this. There's a heavy seed there, and there's a tail over here, and there's a membrane that extends out this way over here. This area is quite dense, and this area is quite filamentous over here. And if we calculate what the center of mass of this object is, you can do that quite easily with just photographic techniques. The center of mass is going to be right about there, right towards the edge of the Samara. Now, when you drop it in the correct way, what happens is that the tail acts like an airfoil. And what you end up with, if you look at this in cross-section, here's the seed, and this is the tail looked on sideways. You get an angular rotation of this going down to the ground, and it spins down as if it was a helicopter. And as it spins down, this tail generates lift and helps slow the descent. Now, biologically, the reason why this is probably important to the tree is that air is never still in forests. The helicopters will come down normally in a straight line with respect to gravity. Here's the tree over here. But if you have any kind of a wind going on, and you frequently have winds, then the Samara will go down at an angle depending upon the magnitude of the wind. And this is useful for helping disperse seeds from the parent tree. And the further you disperse seeds from the parent tree, the more likely that seed is to germinate and form a regular tree, a mature tree. Now, there's some interesting things about this. This means that the Samara has both downward motion, and it has rotational motion. And depending upon how the seed drops, you can get either one or the other predominating. If, for example, you drop the seed like this, so that the seed is at the bottom and the tail is pointing up, what you have here is that you have a center of mass that is located there, and it's being pulled down by gravity, and what you're going to end up with there is something that's almost purely translational momentum there. In other words, the thing will drop like a stone. Now, if you look at some of the detailed structure of the margin, I'm just going to zoom in here a little bit so we can get a better feel for it. If you look at the detailed structure of the margin, you can see it's cut in size with all kinds of interesting little projections. And if you turn it up on its side, you can see it has some interesting curvatures to it. And what will happen in the case of our seed that's dropped is that those projections will cause a side-to-side motion as it drops, and eventually it'll go into the helicopter mode. On the other hand, if you drop the seed like this, with the head pointing up and the tail pointing down, what has to happen now is that you have to impart a rotational motion to it initially so that it comes down and the center of gravity is actually where it should be, below the rest of the Samara. And so when you drop a seed in this orientation, you are imparting to it not only a degree of translational momentum, but you're also imparting it to it a degree of rotational momentum. And when you do that, initially, that rotational momentum will start the seed spinning, and it will come down as the helicopter for more of the distance from the tree down to the ground. Okay, now we're going to have a short demonstration of this right now, and we're going to have more demonstrations later. Ross Jacob is sitting up on a ladder above me right now, and he's going to drop two Samaras one after the other. The first one he's going to drop is going to be in this orientation, and we hope that it's going to come shooting down like a rock, as I said it would. Okay, Ross, ready? Go. Okay, now you might have seen that it started to drop and then started spinning, as I said it would. Let's try that one more time. Okay, drop it that way. Okay, well, it's not cooperating as biological things normally do, but the essence is going to be in the comparison. Let's now take a seed and drop it in this orientation right here. And when I tried this morning, it started spinning almost immediately. Okay, Ross, ready? Go. Okay, well, let's try the spare. Let's try that one more time. Okay, again, it's dropped with the seed up, and it starts spinning almost immediately. Okay, so now we're going to demonstrate that in more detail in a little bit, but that's basically what's operating here. All right, now let's come back to our discussion of rotational momentum and rotational kinetic energy. Let's come back to our collection of Samaras over here. Okay, now these are going to have not only centers of mass, but they're also going to have different first moments of inertia. Let's take this one, for example. This is quite an interesting one because one of the seeds is